Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer architecture. So, we have looked at some of the basics of computer architecture. We have looked at in the previous class, we looked at how control units are designed. So, when talking about control unit design, we have looked at how the data path has to be identified, how the data path has to be defined, and how we identify different elements for the data path. And then we have also seen how the control signals have to be generated for any given instruction to be executed. So, we looked at a simple instruction set, and for that instruction set we saw how the control unit design can be successfully done. What we will do in today's lecture is the following. We will look at some performance issues. So, we have already designed some control unit. Now, we will look at how good the performance of that control unit design is, and we will see how we can improve the performance. Specifically, we will be looking at something called pipelining. So, that is what we will focus in today's lecture. Now, this is a picture of what we have already done in the previous class. Just for a quick recap, let us see what we have here. Remember that we have 5 stages. We have the 5 steps that are required for the execution of any instruction. So, we have to fetch the instruction, decode the instruction. When we decode the instruction, we will have to read the registers, and then we will have to perform the ALU or whatever operation has been given, and then we will have to access memory if required, if it is a load or store instruction, and then we will have to write the result back into the registers. So, these are the 5 different stages that we have. So, now for this we have seen how this entire architecture has been developed. So, we will start with the PC and the instruction memory. This forms our instruction fetch stage. The PC is the program counter. We have the necessary logic to increment the program counter, right, or add a new value in the program counter depending on what is the instruction getting executed. So, if it is a control instruction such as a jump or a branch on equal instruction, then we know that a new value has to be loaded into the PC. Otherwise, the previous value is incremented. Okay. So, we add 4 to it in order to point to the next instruction. So, this part is our fetch part, and then the decode and the register reading happens here. So, decode happens by looking at the different bits of the instruction, and the different bits of the instruction give us various pieces of information which are required for instruction execution. And then we get the register numbers that need to be read as well as the write register. If any register has to be written, that information is also obtained over here. And the opcode information also goes as input to the control block, and from the control block the various control signals required for the various operations are generated. Then of course, the data which is read from here is fed to the ALU. Now, the ALU we said is used not only for arithmetic and logic operations on operands, but also for calculating the addresses, the effective addresses in the case of a load or a store instruction. So, if it is a load or a store instruction, what we have here is in this ALU, you will have the address and the offset that are being added. So, what is being added actually is controlled here by this mux, and then that result is given to the data memory here. Now, we have 2 pieces of memory, the instruction memory and the data memory. So, data memory is used if it is a load or a store instruction to either read the data or write the data. So, if it is a load instruction, the data that is read here is the one that is now written back into the registers. Otherwise, if it is a ALU operation, the data from the ALU will be written back to the register, and we have the control for all these things which are generated. So, this is what we looked at in the previous lecture. Now, let us look at what was the performance issue that we identified in the previous lecture itself. So, you can see that the time that is taken here, okay, we have assumed now that this whole thing takes place, like for instance, as one block. So, one instruction comes in, all these things have to be completed before the instruction gets executed. So, given that situation, so you can see what is the longest delay, longest time that will be taken. Okay, for different types of instructions, they will take different amounts of time. So, longest delay would determine the clock period that we can use. That is, we are assuming that this whole thing takes place in one clock cycle. So, we have to find out what will be the longest amount of time that it will take. Obviously, we know that different paths are excited for different instructions. So, the instruction that takes the longest path, right, that will be the one which determines the maximum time that it takes for an instruction to execute, and that will be the time that we will have to choose for the clock. Okay. So, we say that the longest delay determines the clock period. Okay. So, which is the critical path in this case, in the example that we have taken, it is a load instruction, because remember, for a load instruction you need to access the instruction memory, then the register file, then the ALU for address calculation, then the data memory for accessing the data as such, and then again the register file for updating the register. Okay. So, we find that this will give us the longest path that we have. So, the amount of time it takes to do all these operations will be the time of the clock period. Okay. That is how we will have to fix the clock period. Now, there are other instructions which may take little less time, but normally it is not feasible to vary period for different instructions. So, we will kind of fix it for the largest clock period, largest instruction, and that would be the clock period that we would fix. Now, let us say we want to improve the performance. Okay. So, one of the standard techniques that is used for improving performance is what is called as pipelining. Okay. So, let us look at what we mean by this pipelining. We will take some example. I will take some analogy here. For instance, what we are taking here is a laundry kind of a scenario. So, let us say for instance, washing clothes and then drying them and so on, we are using some machines to do that, let us say. So, if we are doing that, assume that the entire task of washing the clothes and then taking them out, drying them, all these things put together consists of 4 different tasks. You can see that there are 4 different blocks given here. Each of these 4 different blocks indicate the 4 different subtasks which are involved in the washing using the laundry. Okay. So, now let us assume that each of this takes about 1 hour to do. Okay. So, if you start at 6 p.m. okay, and you had a single machine that you are working on, you have clothes coming in continuously to be washed. So, what is it that you would do? You first put it into block A, okay, then it goes into the next block, then to the next block, and then to the next block. So, this takes 1 hour, this takes 1 hour, this takes 1 hour, and this takes 1 hour. Okay, or let us say for instance, okay, I have used half an hour here. Okay, so half an hour for each of these blocks. So, 2 hours to finish up the entire job. Okay. After this 2 hours is over, now you can start with the next load. Okay. So, assume that you have got load A, load B, load C, load D coming in. So, one load is over, next you start with the next load. Now, the next load starts at 8 o'clock and ends at about 10 o'clock. Now, again at 10 o'clock another load will start and it will end at 12 o'clock and so on. Okay. So, this is how the job keeps going. Now, you can see that I can actually do it faster than this, because I identify, or you can note that once this blue block has been done with. Okay. So, at 6:30 this is free. Okay. So, what I can actually do is, now I can bring my new load and load it into this blue block, okay, at time 6:30, because at 6:30 now, while this white block is working on a previous load, this blue block now can start working on this new load. Okay. So, if I have these 4 different blocks, therefore, once this fellow finishes his job and passes it on to the next block, at that time this becomes free. So, now by that time this blue block would have finished its work. So, it will pass on its work to this white block, and the blue block can now take up another piece of load. Okay. So, you can see that after every half an hour, once the blue block becomes free, it becomes free to take up a new job. So, at the end of 8 o'clock, if you see for instance, the blue block has actually finished working on 4 different loads without being idle in between. Okay. In this case, in the previous example where we said we looked at a sequential usage of the different blocks, we find that here you will see that once the block finishes its work, it is idle for about 1.5 hours, and then again it gets used for the next half an hour. Okay. Again it is idle. Now, the same thing is true for each of the blocks. So, what we are therefore trying to say here is, if I pack it up a little more efficiently in such a manner, in this kind of what we called as a pipelined manner, okay, we can see that the total time that it takes to do the complete job can be reduced. So, you can see that you start at 6 o'clock here, the first job will still take 2 hours to complete. Okay. So, it starts at 6, ends at 8. The only difference is now the second job will start at 6:30 and end by 8:30, instead of starting at 8 and ending at 10 as in the previous case. So, third job will start at 7, therefore, it will finish at 9. Fourth job will start at 7:30 and be done by 9:30. So, for the 4 jobs, if we had started at 6 o'clock, we would have gone until 2 o'clock in this case. Instead, now if we start at 6, you will be done by 9:30. So, you can see that total time that is taken to do the jobs can be reduced drastically. What does this require? It requires the fact that you need to have independent units like this, which can be used simultaneously to work on different objects or different loads. Okay. So, you can see how much faster we are able to do if we do this. Okay. So, we use a performance measure called speed up normally. Now, you remember what is speed up? Speed up will be the time taken on an old process divided by the time taken by the new process. Okay. The old process is our non-pipelined mode that you are looking at over here. So, in this mode you can see that it took us from 6 p.m. to 2 a.m. which means it is almost 2 hours per task, therefore 8 hours to do the job. Okay. Whereas, in this new pipelined model that we have looked at, we started at 6 p.m. ended at 9:30 p.m. So, this took us only 3.5 hours. So, from 8 hours we have reduced to 3.5 hours. So, what is the speed up we get? So, 8 divided by 3.5. So, we get about 2.3 times speed up in this case for this example. But actually if you look at how fast you can go with this kind of a process and how much of speed up we can get, you will see that if we do this non-stop, okay, keep on doing it continuously, okay, you will find that every half an hour, okay, one job is getting completed. Okay. Now, though the time taken for a single job is still remains the same, right, the time taken still remains the same, it is still 2 hours, but at the end of every half an hour one job is getting completed. So, you can see that depending on the number of stages, as we call them, okay, we call these at different stages, depending on the number of stages. If there are 4 stages, I will be able to get a speed up of 4. So, in general we say that the speed up will be equal to the number of stages that you have in this pipeline. So, why are we calling it as a pipeline? This is very similar to factory kind of scenario that you may be familiar with. So, you will find that when we talk about automobile industry and so on, where we have things manufactured or different vehicles being manufactured, you will find that they use what are called as pipelines. So, you will have different parts being manufactured by different people and different things being fitted onto the automobile, and all this will take place simultaneously, one after another, it will keep happening. So, that is a similar scenario we are looking at over here. So, we look at each of these as different stages. So, if you can divide the entire job into a number of stages and each of these stages can operate on different pieces of data at a given point of time. So, for instance, at this point of time if you look at all the 4 different blocks are active, 4 different stages are active, but they are working on different pieces of the data. Okay. So, if we can do something like this, then you can see that you can speed up the entire process. Now, this idea is what we try to use when we are looking at instruction execution as well. Okay. So, let us look at how this will work for an instruction execution scenario. So, now let us come back to our MIPS pipeline. Okay. In our MIPS architecture, as we said, if we have to look at it in the form of a pipeline, what will be the stages that we have? So, we already saw that there are 5 different steps that are involved. So, we can almost divide each of these steps into, we can call each of this step as a stage. So, in which case the 5 steps will correspond to 5 stages. So, 1 step per stage. So, what are the 5 stages? Therefore, we first have an instruction fetch stage. Okay. So, this is our fetch step, which will be instruction fetching from memory. Then we have what is called as the decode stage, where we will do the instruction decode and also reading of the registers. Okay. So, we call this as our second stage. The third stage is the one where we will execute the operation or calculate the address. In case of a load or store instruction, we will calculate address. So, EX stage is when the actual ALU operation is taking place. Okay. That we call as the EX stage. Then we have the MEM stage, which was used for accessing memory operands. Okay. This is accessing the memory. And then we call a write back stage, which is used to write the results back to register. Okay. So, we can see therefore that in our MIPS architecture, we can divide the entire instruction execution process into these 5 stages, okay, and then use these 5 stages in a pipelined manner. If we are able to divide instruction execution into these 5 stages, we are expecting that we will get better performance. So, let us see how that will happen. So, let us take some numbers here just to understand what will be the performance benefit that we can get. Okay. So, assume the time for these stages as follows. Let us say it takes 100 picoseconds for register read or write and 200 picoseconds for other stages. Okay. So, if we assume this, now let us compare the pipeline data path with a single cycle data path. Okay. So, let us take for instance a load instruction. For a load instruction, now remember these are the various operations that need to be done. Fetch the instruction 200 picoseconds, then we will read the register which takes 100 picoseconds, ALU operation to calculate the address 200 picoseconds, memory access another 200 picoseconds, and then you will write the value into register, so 100 picoseconds. So, total time taken for this is 800 picoseconds, let us say. Okay. So, this is 800 picoseconds. Now, For a store instruction, let us see what will happen. Store instruction will have these 4 stages, right? Instruction fetch, register read, ALU operation and memory access, because once you store it, you are storing into memory. Okay, so there is no register write operation for a store. So it will take altogether 200 plus 100 plus 200 plus 200, 700 picoseconds. Now it is an R format register kind of a register based operation. So then it takes 200 picoseconds for the instruction fetch and then 100 picoseconds for the register read. ALU operation takes another 200 picoseconds, no memory access here. So only a register write which takes another 100 picoseconds. So it will actually take 600 picoseconds. A branch on equal, there are only 3 operations that need to be done. 200 picoseconds for fetch, register read takes up 100 picoseconds, ALU operation will take 200. So this will take up 500 picoseconds. Okay. So we can see that longest time is for the load 800 picoseconds. Let us look at how the single cycle performance will be and how the pipeline performance will be for this load instruction. Okay. So since this is the longest time taking instruction, let us assume that we have this long instructions coming one after the other. Okay. So which means I have a load followed by another load followed by another load. Okay. So in a single cycle non-pipeline scenario, let us look at what will happen. From time 0 to time 800, 800 picoseconds will be the time taken for this single instruction, for the first load instruction to be executed. So it will start at 0 and end at 800. Stages you will have here will be instruction fetch, register read and then ALU access, ALU to execute the instruction, execute the addition of values for the address, and then you have the data access and then the register write. Okay, so 800 picoseconds. This is followed by another 800 picoseconds for the next load instruction and then at 1600 the third instruction will start. Okay, so the single cycle, if you assume the single cycle architecture, this is what you will have. Now if you pipeline it, let us assume that we are pipelining it with a clock cycle of 200 picoseconds. Okay, so which means every 200 picoseconds a new instruction will be fetched and brought into the pipeline. Okay, so you have this load followed by another load followed by another load. So once our first stage, instruction fetch stage completes fetching the first instruction, it can pass it on to the register reading stage, and you can see that in the next clock cycle, right, that is the next 200 picoseconds, the second load instruction can be fetched. So you can see what is happening here. So the first instruction starts at time 0, okay, and gets executed. Okay, you can see the first instruction finishes at 900 picoseconds. We will see why it is taking 900 picoseconds here shortly. Okay, and then the second instruction, the load instruction, starts at 200 picoseconds and goes up to 1100 seconds. So you can see that instead of taking 800 picoseconds for a single instruction, it took a little more than 800 picoseconds. Okay, it is taking about 900 picoseconds. Now why is it taking 900 picoseconds? If you look at that, you will see that when I start this second instruction, load instruction, now this will take 200 picoseconds for it to get completed, because the instruction fetch part takes 200 picoseconds. So even though the register reading, right, the register reading takes only 100 picoseconds, you cannot start next register reading until the instruction fetch has been completed, right. So you will see that there is actually a small, though you have 200 seconds available, only 100 picoseconds of work actually is done during that time. So during this 100 picoseconds nothing is getting done, and during this 100 picoseconds the register read takes place. Okay. So because of this 100 picoseconds which is wasted here, okay, you will find that instead of stopping at 800 picoseconds, I will stop at 900 picoseconds. Okay. So that is a small penalty you may have to pay. Okay, but typically if you divide the instructions into stages of equal amount of time, then you will find that without any problem you can just keep going through the pipeline. Okay. So in this case, because all the other stages take 200 picoseconds and except the register read and write which take up 100 picoseconds, we are dividing it up into 200 picosecond slots. So you will see that overall time taken will be accordingly based on the 200 picosecond slots. Okay. So you can see what is happening here. Okay. So now look at when your next instruction can come in. The next instruction can come in after 400 picoseconds, because by that time the second instruction has been fetched by the instruction fetch stage, and the instruction fetch stage now becomes free to do work on the third instruction. Okay. So if you look at what is happening here, you will find that next 200 picoseconds will be instruction fetch, next 200 picoseconds register read, next 200 picoseconds ALU operation, and then next 200 picoseconds will be the data access, and then the next 200 picoseconds will be the register access. of course, out of which of course we are assuming that the register operation may be over in 100 picoseconds, but effectively you have time available until this 1400. So, 400 to 1400. It is very simple to understand this. 200 picoseconds we are fixing for each stage, and there are 5 stages. So, total time taken will be 1000 picoseconds. So, 1000 picoseconds for doing each job, but every 200 picoseconds you find that one new job is getting completed. Okay. So, that will be the benefit that you get out of pipelining. Time taken to do the actual job is not changing, for each instruction does not change, but the number of instructions executed per second, that is what is changing. Okay. So, we say that whenever we do pipelining, the throughput will improve, that is the total number of instructions executed per second will improve, and therefore, the overall execution time will improve. Okay. So, that is the benefit that we get out of this pipelining. So, now if you look at the speed up that you can get out of a pipelined execution. Okay. So, if all stages are balanced, what do you mean by balanced? What we are saying here is that all of them take the same amount of time. For instance, if all of them take for instance 200 picoseconds as we looked at in the previous example, then the time between instructions pipelined is the same, then you can find the speed up as time between instructions non-pipelined divided by the number of stages. Okay. So, the time between instructions pipelined, okay, will be equal to time between instructions in a non-pipeline stage divided by the number of stages. This is if the stages are balanced. Going back to the previous example, in the non-pipeline stage, if we say it takes 1000 picoseconds and we have 5 stages, now time taken between instructions in the pipeline stage will be 200 picoseconds. Okay. So, if it is not balanced, then the speed up will be a little less. Okay. But normally we try to balance the stages so that it becomes easier to do the design. So, for our practical purposes, we can assume that the stages are balanced, therefore, you get a speed up which is equal to the number of stages. Okay. So, if an earlier program had taken 1 second to execute, now it will take you 1/5 of a second to execute. That is the kind of speed up that we expect, okay, once we do this pipelining. Okay. What we of course need to remember is the latency or the time for each instruction does not decrease. Okay. See, as we saw here, each instruction will still take those 900,000 picoseconds to execute. Okay. Only the overall time taken will be reduced because we are overlapping the execution. So, now let us look at how the MIPS architecture can be looked at in terms of this pipelined design. Okay. Now, there are certain things that we need in order to make this pipelining possible and make pipelining easy. Okay. Now, if you look at the MIPS instruction set architecture, you can see that it is actually designed for pipelining. Okay. Now, what are the features that help in this pipelining? If you look at that, one of the features of MIPS is that all instructions are 32 bits. Okay. So, the advantage of having all instructions as 32 bits is that it is easier to fetch and decode in one cycle. Okay. So, you fetch the instruction and you are able to decode it. Okay. Both this can take place in one cycle. Whereas, for instance, just for a cross reference, if you look at the Intel x86 architecture, the instructions can be from 1 to 17 bytes. That is, you have 1 byte instructions as well as 17 byte instructions. So, different amounts of time it will take to fetch these different instructions. So, pipelining such instructions becomes a little difficult. But if you have all instructions of the same 32 bits, you know that all instructions can be fetched in the same amount of time. So, dividing it up into stages and saying that this will happen in each stage becomes easier. Okay, that is one of the first features that we look at. Second feature in MIPS is that we have very few and very regular instruction formats. So, having very few instruction formats again makes it easier for us to do the decode correctly, okay, decode in an easy manner. Because if you had different instruction formats and each instruction had to be interpreted differently, then the time taken for doing that would be more. So, now the very fact that you have very few instruction formats and they are very regular, very easy for us to decode the instruction and read the registers in one step. So, which is why in the second step called instruction decode stage, we do both the decode as well as reading of registers. So, it actually becomes an operand read stage as well. Okay. So, that is our second advantage. Third is the way the load and store addressing are done. Okay. So, the way load store addressing is done in MIPS, we calculate the address in the third stage and you are able to do the memory access in the fourth stage. So, this is another advantage that we have. And the fourth feature that we use in MIPS is that the memory operands are aligned. So, what we mean by this is that all memory accesses take exactly one clock cycle. So, we are assuming that 32 bit can be accessed in one clock cycle, Therefore, all the memory access can be done in one clock cycle. So, with these simple features, what MIPS provides for us is that it allows you to do the pipelined design in an easy manner. So, to summarize, let us look at what we have covered in today's lecture. So, what we have looked at is that the concept of pipelining can be used to improve performance. So, what does this pipelining essentially mean? You basically take a task and divide it into independent subtasks, and we start one subtask as soon as the previous finishes. So, this way new jobs can be taken, and as one subtask moves on to the next job, right, the previous one, the first subtask can start working on a new job. So, that is, for instance, if you have a series of jobs coming in, as soon as one subtask finishes on job 1, it passes it on to subtask 2, and subtask 1 can now start working on job 2. Okay. So, if you keep doing things in this kind of a pipeline manner, we saw how it leads to some kind of a parallel execution, and that will overall improve speed up. And we also saw that the speed up is through improvement in throughput. Remember, the time taken, the latency of each job still remains the same, okay, but the number of jobs completed per second become more. Okay. So, that is what we mean by throughput. So, throughput is the improvement that we see, okay. And we also see how this idea of pipelining is used in the MIPS pipeline. So, the MIPS pipeline can be divided into 5 stages: the instruction fetch, decode, exe, memory, and the write back stages. So, once we divided into these 5 stages, we saw how the pipelining can be effectively done in MIPS. So, we will look at details of how the pipeline is implemented and other issues that come up when pipelining is done in later classes. Okay. So, questions to review today's material. Question number 1, what is meant by pipelining? Question number 2, give examples of pipelining in real world environments or in real life situations. Question number 3, how is the instruction execution in MIPS pipelined? Question number 4, how does the number of stages in a pipeline affect performance? Thank you.